this week, I'm very pleased to introduce Richard Magin. So I know several people here have asked about this fractional calculus as a topic. And people were also asking about more talks on applications to medical physics. So we actually have both here. So Richard has worked on a wide range of things, but one of the things that he's well known for is he wrote the book on fractional calculus and applications of fractional calculus.
Yeah.
And there's particular places where that's useful in the sort of medical and bioengineering, which he's an expert on. And he's going to talk to us today about some of those things. So it's all yours, Richard.
Oh, thank you. Let me minimize the window here. And can everyone see my pointer going round and round, I hope?
Yeah.
Okay, good. I'll get, so thank you. Whoops. Okay. First, I'd like to thank Professor Douglas Scott for the invitation to speak to you today. And I wish, we've been talking COVID things, I wish I could come visit. I've been to the campus once years ago. It's beautiful. And I'm sorry I missed another opportunity to visit, but maybe in the future. So today I'm going to talk about diffusion-weighted magnetic resonance imaging and show how we are able to use a fractional diffusion equation to encode the complexity of brain tissue, white matter, gray matter, and hopefully in some cases, the constituency of brain tumors as a tool for diagnosis and monitoring treatment. So as a summary of my talk, I picked up this cartoon from Punch and I keep using it. Gentlemen and gentlewomen, this is just to give you an idea. Actually, there are lots of wires and things. And that's definitely the case with what I will do today. I think with giving talks, you can pick one of three. You can try to inspire, you can try to inform, or you can try to impress people. I'm going to shoot for the middle one. So, summary of the talk. The basic idea is to show how fractional calculus models of relaxation and principally diffusion can capture the complexity of brain tissue. So what we're doing is we're going to look at the Brownian motion of the water in biological tissues, use a fractional order time and space version of the diffusion equation to model the dynamics of the water in magnetic resonance imaging, so that the images that you get of the brain, for example, will have a contrast that is sort of coarse graining the subvoxel structure. So you little see, I'll show you better pictures later, but you'll see little pictures where there's color maps and each pixel has a unique property. And we try to get those properties out of the local diffusion of the signal in the different compartments. Or to use a picture, instead of using integer calculus where we have 1, 2, 3, whatever orders, with a fractional calculus, you have an adjustable wrench. We down here call it a Phillips wrench. At least my dad always told me it was a Phillips wrench, but you probably call it some kind of spanner up there. Anyway, so here's an outline. I'm going to first provide a little context for fractional calculus, as Douglas was hinting, how it appears in magnetic resonance and how the two are connected via stochastic processes. Then I'll go on and talk about connections, relaxation, diffusion, and then how I'm trying to use some phase diagrams to make sense of it to myself, and then some conclusions. So for context, can't beat a Venn diagram. Magnetic resonance, fractional calculus, random processes. Magnetic resonance, principally the nuclear magnetic resonance that is the basis of MRI, is in the part of the magnetic behavior that's influenced predominantly by the water will be the subject. And the diffusion of that water can be modeled quite completely with fractional models. And these are generalizations of the Brownian motion. One of them is called the continuous time random walk, and another one is a fractional motion or fractional motions models. But these are, again, an intersection themselves between the molecular motion, diffusion and relaxation. And the diffusion and relaxation go right back to MR, because the T1 and T2 relaxation times and the diffusion coefficient are readily available for water that is hindered and restricted as it moves in and out of the organelles and membranes and blood vessels in the tissues of the body. So I went backwards. I want to go forward. Just to give you a place to start, if you start thinking about things, before I show the explicit connections. The book's a little old, but it's a good one. This is Hilford's book, Fractional Calculus in Physics. So if you're looking for applications of fractional calculus far away from the galaxies that some of you work in, this might be a good place to start. Others have applied fractional calculus to electrochemistry, to viscoelasticity, and to dielectrics. Typically, processes that exhibit behaviors over huge orders of magnitude in terms of frequency or time, with creep and relaxation and viscoelasticity, with the dielectric relaxations in polar and molecules, and in electrochemistry. So we're going to, though, try to extend it and look at it within the domain of magnetic resonance. And we're going to limit ourselves to the principal area of magnetic resonance imaging, MRI. Some people do some things with NMR. As far as I know, no one's doing much with electron spin resonance with fractional models. Typically, the fractional models, as you'll see, come up when the processes that you're looking at are multi-exponential or anomalous in that the diffusion is non-Gaussian. So we'll look at relaxation and we'll look at diffusion within MRI. The classical way to look at relaxation is to look at the Bloch equation, look at the relaxation in terms of T1 and T2, and the first order, it's exponential for each compartment that you're dealing with. With the fractional generalization, the multi-exponential behavior is described sometimes by a stretched exponential, sometimes by a generalized exponential called the Mittag-Leffler function. And this introduces not only the T1 and T2, but it gives you a third parameter, this alpha, which is the order of the Mittag-Leffler function. When that order is 1, it becomes an exponential. So this is your adjustable wrench to grasp the problem. With diffusion, the classical model is Gaussian diffusion models. It's a direct measurement of the diffusion of water. In simple systems, it's used in chemistry and physical chemistry all the time. In clinical medicine, it's used typically in the domain of diffusion tensor imaging, where one takes the diffusion coefficients in tissues that are anisotropic, white matter, for example, muscle, skeletal muscle, cardiac muscle, any tendons, ligaments, anything that has a principal axis, you can orient your data collection so that you can look in those directions and then diagonalize the tensor and gain information about the structure. There are tissues where the complexity isn't a simple matter of anisotropy. The behavior shows up as non-Gaussian, typically as described by a mean squared displacement that is increases with diffusion time in a sub or super linear manner. That is, it goes up order greater than t or less than t. As I mentioned and showed earlier, if you generalize the underlying diffusion equation, the classic heat equation for the probability of the water to move a particular place at a particular time. If you generalize the space and time derivatives using the fractional versions that go by the names of the promoters or inventors or popularizers. Caputo for the time derivative and Rees for the space derivative. What you get is the diffusion coefficient again, and you can do it anisotropically if you wish, but you also get an alpha from the space derivative and a beta from the time derivative, depending how you go about naming them. Okay, so I've told you a little bit about the context, a little bit about the connections of MR with relaxation and diffusion. So in the next two sections, I'm going to try to talk specifically about how the fractional equations modify the exponential and Gaussian behavior. For the relaxation case, we will look at basically this overlap here between magnetic resonance and random processes. And we'll look at relaxation where it follows a typical multi-exponential behavior. When I started talking about fractional calculus, I always spent the first 5 or 10 minutes trying to define it quickly and showing equations. And that just either put people to sleep or scared them to ever want to do it. So now I just show the books. This book I'm showing because it was the first one of the first ones I ever saw. It was first published in 1974. It's out in a Dover edition in 2006. It's Oldham and Spanner to anybody who does fractional calculus. And Keith Oldham is at Trent University in Peterborough the last time I talked to him, which was pre-COVID, and I'm scared to look him up right now. But yeah, it's a good place to start. So the Bloch equation is the governing model for the bulk behavior of paramagnetic and ferromagnetic materials for that matter. But we're going to talk about it as a set of equations where the magnetization evolves in time with a cross product term that is typically the precession term if the B of t here is constant. And after, but if that B of t is a radio frequency field anywhere near the Larmor equation, the Larmor frequency, B0 gamma, then you have, oh, it's so nice talking to physics students. I have to stop and it takes whole paragraphs to talk about that stuff. Anyway, but if the applied field is a radio frequency field, then you can generate a precessional motion and you can reorient this magnetization. And you can perturb the system for a short period of time, a pulse, as they say. And then as the system returns to equilibrium, it follows a T1 and T2 relaxation. The T1 typically along the orientation of the B0, the static field, right up the axis of an MRI machine, and the transverse components in the perpendicular plane. And these are thermodynamically manifestations of the fact that the spins are going to orient in every possible way as soon as they can. And so T2 is more or less a second law of thermodynamics with the maximizing entropy. And T1 is a first law thing where the system is just returning to equilibrium. And so it's returning to its initial orientation. So I guess I could have shown this first and I had to tell you, have you guess. But the gyromagnetic ratio is the gamma. The B of t is the external field, and it typically in MRI, it has a static field in Tesla, typically 1.5 or 3, radio frequency field, and then a number of additional gradient fields where you boost the B0 component in the Z direction for short periods of time, and then all kinds of relaxation stuff. The net result is you can actually change the orientation of this M. And I was reading a book by Robbie that I had not read. And it turned out he was the one that figured all this stuff out back when he was playing with beams of particles traveling through magnets before World War II. It got him the Nobel Prize, but I didn't realize that this spin dynamics was basically his invention. So the idea is that you take the system that is precessing about the z-axis here, and you rotate the magnetization from the Z equilibrium state down to the y-axis, and you do it quickly in picoseconds. And then after you're done, the system follows T1 and T2, returns to equilibrium. And as it returns, the magnetization in the transverse plane is detected through some time varying M that crosses the oriented radio frequency coils of the system, basically solenoids or saddle coils. And so what you get is you get a transient decay. And the decay of T1 and T2 follows a spiral, and the rate can be measured, and ultimately with MRI you can measure the rate in every imaging voxel. Orders of magnitude here, for a MRI operating at say 1.5 Tesla, the frequencies here are 64 megahertz for water protons. They're different for every other NMR active nuclei. Okay, so the Bloch equation, if we go to the rotating frame, simplifies down to just a straightforward exponential relaxation. The solutions just come out as exponentials. What we do in fractional calculus all the time, for better or worse, is to try to capture multi-exponential behavior through generalization of the order of the time derivative. And so we just allow this time derivative to have an order alpha, in this case between 0 and 1. And this is an alpha corresponding to the T2. And there's another possible, since T2 and T1 are different, there's probably a different order for the T1 relaxation. And so this gives you 2 wrenches. So actually I should have shown more. My first slide wasn't exactly honest. There are multiple adjustable wrenches, and so you have the flexibility of changing the alphas to fit the T2 and changing the betas to fit the T1. One final mea culpa is that the alphas and betas that I've chosen here are not the alphas and betas that I will choose later in this talk. And it's an inconvenient truth that everyone uses their own definition of alpha and beta. So it's like a Fourier transform, where sometimes you've got a 1 over 2 pi, sometimes you got a 1 over the square root of pi, and sometimes it shows up in the time domain, other times in the frequency domain. You need to know your local terminology to follow what goes on. The details about how this works you can find in a recent review article in the Critical Reviews of Biomedical Engineering. You can then find the definitions and more of the details of what I'm talking about. The point here is that we've taken the Bloch equation as it is used in NMR and MRI and generalized the relaxation. And the result is actually pretty straightforward. You can just take the Laplace transforms during and after these pulses, and out pops solutions that have exponentials or Mattei-Leffler functions. If we just assume that the XY component, the T2, was fractionalized, in this case of order alpha, and the T1 was not, you're going to get the growing exponential for the Z component, and you're going to get a decaying exponential, exponential-like behavior for the T2. So here's some spirals where the relaxation behavior as the system progresses, this is time here, this is the X and the Y and the Z components of the magnetization. So right after the initial tipping, you have all the spins along the Y-axis here. When you turn that off in the rotating frame, they start to spiral down. And the rate at which they decay, up to now, had always been just either whatever the T1 and T2 are. But now with the fractional model, you have the ability to change or modulate this behavior. So here you have a T2 set at 50 and here at 100 millisecond. And then the colors correspond to alpha equal 1, exponential, 0.9, 0.8, 0.7. And so you can see that you now have ways of affecting this multi-exponential decay of the system. It may be quenched and decayed quite quickly, as is the case in normal MRI or NMR when you have inhomogeneities in the magnetic field, the so-called T2 star. But this goes on a long time. It just doesn't shorten things. So you can stretch out behavior sometimes. You can also apply these models to the underlying physics definitions of what these T1s and T2s are. And that's the classic paper by Bloomberg and Purcell and Pound. And those models are developed with integer calculus, and they can be generalized to fractional order. And then the idea is to apply this to tissues. I was just looking online before the talk at a paper by Spencer and Reeder, where they were looking at ligaments and tendons. And the time constants for these assemblies of collagenous tissues are 10 milliseconds, 100 milliseconds, 1,000 milliseconds, all mixed together. And it's very hard to make sense of it, but these fractional order models allow you to identify each of those components. But they didn't have any pictures, so I didn't bring them. So, but that's something to keep an eye on. Okay, so that's all I'm going to say about relaxation. I'd like to talk some more about diffusion, and then try to show some clinical data to go with it. So for the diffusion, we go back to the MRI, fractional calculus, random processes, and I've just filled in some of the many names that most of you are probably familiar with from studies of statistics, Brownian motion, diffusion, NMR, and maybe not so familiar with the fractional calculus circles, but the names of the researchers go back to literally the discovery of calculus. It's Riemann, Louisville. I mean, everybody who's anybody in NMR, I mean not NMR, in analysis and in calculus, used in some form fractional calculus. If you're interested in the diffusion modeling, using a good place to start is this recent book by Evangelista and Lévy. And these friends of mine actually do a nice job of looking at the complete spectrum of models. Okay, this is the slide to pay attention to. This is the gist of what I want to get across. That what we'd like to do is basically coarse graining. We know we're looking at a brain. This is not a human brain, but it's an animal brain, and it's been fixed. And typically, if you want to know what the brain looks like, you have to slice and dice it and look at these 5-micron slices with resolution at sub-micron. And look, in this case, you're looking at maybe some cross sections of some white matter. And then you model these slices as some combination of cylinders of different diameters and different distributions with different permeabilities. And then you turn loose Avogadro's number of Monte Carlo simulations to try to work your way out of what that water is doing here in those compartments. And then try to see if what you predict fits what you measure by slicing virtually the brain and looking at diffusion-weighted images where you change the diffusion encoding pulses and the time between the pulses. That gives you a measure of basically the characteristic function of the probability, the stochastic process that's undergoing. So what we do is try to fit these two together. We try to fit the simulations and the mathematical models together with the images so that we can then take an image with maybe sub-millimeter isotropic voxel resolution. In this case, it's a cross-section of the corpus callosum. And you can see the little speckles here correspond to regions that have higher or lower values of diffusion coefficient, or higher and lower values of alpha and beta, or higher or lower values of the density and diameter, or the distribution of diameters of the white matter fibers. So this is all worked out by Danny Alexander at UCL, and it's very well described in his NMR and Biomedicine paper. Okay, in order to get diffusion, we have to append, we don't do it, actually, Torrey did it, and he did it early. I mean, there's no moss growing on these rocks that are the foundation of NMR. A lot of the things I'm talking about, maybe not fractional calculus, I haven't found that in Purcell and Bloch's papers, but almost everything else is in something that Robbie wrote, probably. But particularly what Torrey did was just add the diffusion. He said, if we've got this magnetization, it's a bulk property that we can measure using radio frequency signals and pulses, then we ought to be able to keep track of how these magnetizations in each of these compartments moves with time, particularly if the tissue is perfused with flowing blood, and if the blood is flowing at a velocity, say u, or if the tissue has multiple compartments, like the white matter, gray matter, or muscle compartments. And then the diffusion is going to be a process that will carry signals and information about the structure. So the way this is done is in a normal pulse sequence of tipping the magnetization 90 degrees to align it along that y-axis I showed you, allowing the spins to diffuse for a while and to get out of sync because the fields are never perfect, applying a magical 180 degree field that flips the spins over so that after an equal time, they reassemble transiently in an echo, and this spin echo then provides the free induction decay that is the Fourier transform of an image in MRI. It also has information in its amplitude that's related to the diffusion. If in addition you apply this transient burst of magnetic field in the z direction to yet another set of coils. So I wasn't kidding when I said there were lots of wires and things in the background. These are, I used to teach in the electrical and computer engineering department in Urbana, and I've got a slide showing the block diagram of an MRI and how that block diagram maps one-to-one with the curriculum and the courses in the curriculum. But the diffusion signal then that we acquire typically is a simplification of this equation. So we go to the rotating frame, we look at the XY component of the magnetization. We have a term that involves these gradients, G of T. We have a term that involves diffusion, and we have a term that involves relaxation. And we can normalize the diffusion, the relaxation term by doing the experiment with and without the diffusion gradients. We can then turn on and off the diffusion gradients at different intensities so that the areas here change. And then this gives us a parameter, the famous B value, which is a combination of the area of the pulse squared multiplied by the gyromagnetic ratio. And then that so-called Q term is multiplied by the effective diffusion time. If the pulses are fairly short, then it's just basically the time between the pulses. So the Bloch equation, as modified by Torrey, adds diffusion and flow. You could do, it's a different set of gradients to get the flow, but works just as well. In the case of diffusion, then you get a signal that decays to first order. In the case of these pulses of this type, and these were pioneered by Stetzel and Tanner, and that gives you a simple exponential decay in the signal. So it's basically the amplitude of the free induction decay here. So if you look at the brain, dividing the brain into cerebral spinal fluid, gray matter and white matter, if you measure this diffusion coefficient, you get decaying exponentials. In the case here, this is a log scale, and this is a linear scale in B. And the cerebral spinal fluid, which is basically saline with some proteins floating around in it, it surrounds all of our axons and neurons and fills the ventricles. It is a straightforward linear decay. So the slope of that corresponds, of course, to the diffusion coefficient. The gray matter, maybe it's multi-exponential, maybe it's just a different d. It's certainly a lower diffusion coefficient because it's a less slope. The white matter, though, is really complicated because it's probably anisotropic, so you're going to have to pick the direction, but it also contains multiple fibers and multiple diameters. And so what you see is this broad distribution here. And so the diffusion coefficient isn't a straight line. So you need to try to capture this curvature. Just plotting it as an exponential doesn't do it. So using fractional calculus, we just go to the block equation and modify the time derivative to the so-called Caputo derivative, and then modify the space derivative to one of these Riesz derivatives. These are generalizations of the integer order operators. And they allow, in the case of the time derivative, you to consider not exactly when you hit the ball or when you kick the ball, but maybe a little bit about the history of the ball and the history of the foot before they came in contact, and to the extent that that might affect the dynamics of the system. With the space derivatives, it is a non-local derivative. It allows you to consider the fact that there may be things other than next nearest neighbor that contribute in some way to a process. And so in both these derivatives, the next nearest neighbor and memory effects are encoded into, as a kernel, into a convolution-like operator that generalizes the derivatives. And what this allows you to do then is to solve these equations, and the solution here comes out in the simple case. Let's just keep the, as we did before, let's just keep the alpha 1, and then let's let the beta be flexible. What you end up getting is since you've left the exponential behavior here in integer order 1, you get an exponential, not a Mittag-Leffler, but because of the beta here, you get actually a BD coefficient that's raised to a fractional power. This is a so-called stretched exponential function, and it's been studied, gosh, since the 1850s by Kohlrausch. And it was often used in the olden days to study the decay of dielectrics, which didn't follow simple RC behavior. What we see here is that this curvature in the beta gives you a way to get at the curvature in this decay here, because when the curvature in this decay curve of white matter shows up here, this is actually pretty well fit if you raise BD to a fractional power. And so what we're able to do with MRI is collect the data. In the case of a human normal brain, me, well, to the extent that I'm normal, and you measure the diffusion coefficient, and then you can then get maps of the beta coefficient. And since you're messed around with the order of the operation here, you got to be really careful. If you want to keep D the way it was in millimeters per second, millimeters squared per second, then you need to have something to keep track of your units. And so you need a space constant. Likewise, if you play with the time derivative, you need a time constant. Units, 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 as we know. Anyway, so I explained all this as far as I understood it years ago in a JMR paper. And what it comes out as is if the pulses are short, you find that the diffusion coefficient follows a general process, and this diffusion is what is encoded when we do the NMR experiment, diffusion-weighted NMR experiment in MRI. And so the actual data that we collect is essentially in K-space, in the Fourier domain, and the decay of each spatial frequency follows time raised to an alpha power, the order of the time derivative, The spatial frequencies are weighted not by k squared, which would be the case if we had a regular second order derivative here for a Laplacian term. And the diffusion coefficient itself has funky units. But as long as you keep the diffusion pulse fairly short, this is actually a really good model for the data. And the nifty thing about NMR, both imaging and in diffusion, is that we don't collect data in the time domain or the frequency domain, or we don't scatter X-rays and collect it, in a reciprocal lattice space or whatever. What we do here is we actually collect the data in the frequency, the QT domain for diffusion. So in this situation, we're able to describe the results of the alpha and beta as a modification of the Gaussian behavior. And the modification goes back to how much you change the diffusion away from the Gaussian point, where alpha is 1 and beta is 2. Always got to keep track of what I'm talking about here. Alpha is the time derivative here, and beta is the space derivative. And anything that happens along this line corresponds to some sort of a quasi-Gaussian diffusion. It's a battle between sub and super diffusion, where the spins are either moving faster or slower, or are trapped or free to move. So this model fits data. This is not me, this is a rat. And in this particular case, we're looking at 3 different regions of the rat's brain. One that's more or less CSF, one that is more or less corpus callosum, one that's more or less gray matter, and one more or less white matter. So this is the gray matter, this is the white matter, and this is the corpus callosum. So we have data collected that fits each of these regions, and we are able to then fit these coefficients, the alphas and the betas, to the decaying data, and then it is the fits on each curve in each imaging pixel that makes the pretty pictures. Okay, you want to see the pretty pictures. So if you look at the slice here, we now get a picture not just of the relaxation time or the diffusion coefficient. That is the diffusion coefficient on a color bar scale for the rat brain. And then here's the alpha map, here's the beta map, here's the mu map and the tau map, because this is the space and time constants we need to keep everything copacetic. And then my student at this time, Carson Ingo, combined everything into an entropy model, where he was able to take this solution to the fractional diffusion equation, treating it as a characteristic function. He just calculated the Shannon entropy of the whole thing and normalized it, and makes really nice pictures. Another colleague of mine, Tom Barrick in London, has taken the model and simplified it even more. He looks at diffusion as occurring along this line diagonally that moves down the phase diagram here. And so he just sets, he takes the general equation for the Mittag-Leffler function with the diffusion coefficient, the Q space term, and the Q squared delta bar is the B I talked about before. The Q is the K-like quantity that has the units of the spatial frequencies of the diffusion path itself. And so this information then, in the case of staying on the line here, you set 2 alpha equal to beta, and what you get is a very nice form where you have a Mittag-Leffler function, where you have now a BD to the alpha. And so this is sort of the natural generalization of the stretched exponential function I showed you earlier. This function is the generalized Mittag-Leffler. If alpha is equal to 1 in the E part here, then you get an exponential, and 1 there, you have the classical case. But here you have both. And Carson also showed that the entropy term here allows you to maybe look at how the landscape changes with variations in the alphas and the betas. So we did this, Tom did it, at 3 Tesla in some normal patients, in some normal volunteers and some patients, made some really pretty pictures of the alpha and beta maps. And what you're seeing here is you can make as much sense of it as I can. I'm not a radiologist, but I can tell white matter from gray matter, and there are some dark regions there that are CSF. So the important use of this, of course, is to try to use it to characterize tumors or dementia or diseases that can't be managed fully without entering the brain. So here are 3 different patients, A, B, and C, from this paper that Tom published last year. And the standard T1 relaxation with contrast agent gadolinium in the 3 cases here has different results. It lights up, it doesn't light up, it's rim around the collar. The diffusion coefficients sort of reflect this in a reasonable way. That is, high diffusion coefficient usually results in faster decay of the diffusion signal, so the signal intensity is less. Lower diffusion here, then you have a higher signal intensity. The alphas and betas, and the alphas in this case, and the entropy that we calculate, and this is the DTI map for this slice, gives you different information about the structure. And it's this contrast that is of interest to the oncologist, to the radiologist, and to us to try to optimize these differences and to associate those differences with changes in compartments, with cellularity, which is a key factor in terms of projecting whether or not a tumor will metastasize. Okay, this never ends. The models just continue to evolve. Mugen Karaman with Professor Zhao here in Chicago used a generalized or different model than the one I just showed you, where the alphas and betas now have slightly different definitions. The B is still Q squared delta, but now the diffusion coefficient is time dependent. And so we're allowing the signal to evolve in time, which is in some way a manifestation of how tissues act as barriers, and that water maybe for short times will be within a cell, and it will sample that environment over a millisecond or so. And then after that time, at 10 milliseconds, it will have escaped from a particular cell. And then it will explore the environment around all the cells for the next maybe 10 or 20 milliseconds. And then it'll start to permeate between the cells and between other regions of other distributions of cells. And that'll get up to hundreds of milliseconds. So as the time goes on, the effective diffusion coefficient changes. And this model seems to capture this. Again, this is some data that Mugen fit, where again, they're looking at tumors, and these are small tumors and small heads because it's pediatric brain tumors, and it's a really insidious disease. The models, though, just get complicated and complicated, and curiouser and curiouser, depending how you want to look at it. And this is, I don't want to look at it this way. This is too complicated for me. You can use the fractional motion model, which essentially now it assumes the diffusion coefficient is constant, but that the diffusion process itself is either persistent or anti-persistent, and that is for whatever reason the spins will continue to move in one direction or anti that direction, and so it gets into a situation where I've found that there are probably too many models. It's almost a one-to-one map between modeler and model that they're using, and yet some of them really work. So my question is, how do we choose which one? And that brings me to sort of the last thing I want to talk about today, which is phase diagrams. Which, it doesn't bring me back to my childhood, but it brings me back to some sad homework sets in physical chemistry. Anyway, So what I've tried to talk about here today is some of these different models in terms of the equations. And here I'm going to try to talk about these models in terms of a plane. This phase diagram with alpha and beta I've been talking about, I'm going to call the z=0 plane of some putative cube. It's really a rectangle, but we'll call it a cube. And so here we have a constant diffusion coefficient, d, beta, and alpha. It's not a function of time or space. And in that plane, we have this quasi-diffusion line here, and we have sort of Lévy motion here, and we have subordinated Brownian motion here. And that process is fairly well understood. But the generalized models that I was just showing you, one whole class of these models allows the time parameter to vary. That is, as the spins move out of and around the cells or the compartments as they're hindered or restricted, this time dependence is explicitly included. And then this model, it turns out, shows up in a different plane, the backside of the cube. And there's another model where you can keep the integer time derivative, but allow the space derivative to be fractional, and the diffusion coefficient to have the same time dependence. And so the model I've talked about most here today is this CTRW model, the fractional motion model. I showed you some of the work that Muge had. And then I haven't talked much about this one over here, where it has a generalized solution of this so-called Kilbus-Sago motion. I mean, the good news, bad news is that these models give you different performance that corresponds to different geometrical regions. And this actually has been explained in another talk that I'm not giving today, but you're welcome to look it up because it just came out as part of a special issue in the journal Mathematics, and it's free. So let's try to tie this together. It's supper time for you. It's past supper time for me. So we have this plane here of the alpha and beta. Here's the time derivative and the space derivative. And the mean squared displacement just goes as 2 beta over alpha. So in the integer case for this model, we have a fractional time derivative, fractional space derivative. When beta is 1, alpha is 2, we get linear time behavior. The other quadrants here of this model correspond to the Lévy motion, subordinated Brownian motion, and then the classical Gaussian situation. And so whether the mean squared displacement is faster or slower, you're either in this region or this region of this phase diagram on the floor of this phase cube. If you look at the back surface and play the same game, this is the fractional motion model, and here you have this gamma alpha plane, and now you have parameters that deal with the correlation of the motion and the fluctuations of the motion. And this has been explained by Elazar and Schlesinger a long time ago. And this gives you a similar time dependence, but it involves different parameters. And so what we have here is we've got the same sort of fractional equation, but if you look at the red one here, you see that the time derivative is integer. The diffusion coefficient is power law in time, and the space derivative is fractional. So these different models give you different performance and different behavior. The last case is this fractional power law here, and this corresponds to the case where you have a fractional time derivative, a fractional time dependence in the diffusion coefficient, and integer space derivative. So these different models all have different behavior, and depending on what problem you're trying to solve, whether you're looking at cardiac muscle, connective tissue, brain tumors, you might anticipate or have histological, pathological information and data collected with a mean squared displacement by varying the acquisition parameters that might lead you to think this model would be better than this model, than this model. But we need to be able to distinguish between them. And so what's necessary, I think, is you have to is collect the data doing the diffusion, just as you do in DTI, but in DTI you have to go further and look in different directions. Here, I think what we're going to have to do is collect data at different Q values and at different diffusion times. And then what that will do is give us the opportunity to tease out which model corresponds best to a particular tissue, a particular histology, and maybe project some information on the pathology. Okay, I think I'm almost done. Conclusions. Just to connect the dots up here, if you don't know already, it's been published in Physics Today several times. Diffusion is anomalous. As I'm finding, and you will find if you start looking under these rocks, anomalous diffusion is mostly everywhere. And surprisingly, the tools of fractional calculus are pretty versatile and pretty easy to use. This work, the clinical work, has been done by colleagues and co-investigators. Muge, I mentioned, Zhou Zhao works with him. Zhuang and Zhu are in Wuhan in China. Guan Yu is a graduate student at UIC. Carson's a former grad student. Hamid's a former grad student. Victor, Matt, and Tom are currently unindicted co-conspirators, and they're part of this special issue that I was telling you about. The special issue is just coming out now, actually. There are papers going in, and so anyone who has an interest in developing fractional methods for MR, it doesn't have to be clinical. It could be diffusion, it could be physics-oriented, material science, but anything that is related, there's a deadline of December 31st. So I thank you for your attention. There is a group of us, Tom and Victor and Matt and Muge and David and Jinjin, who do this stuff. And we have a study group, and we're always looking for new volunteers. But the modeling, the medicine, and the math definitely overlap. And Evan Ozarslan years ago said that extracting structural information from the diffusion attenuated MR signal requires models of biological tissue that link biophysical features of the underlying microstructure to the measured diffusion-weighted image, or the signal. Couldn't have said it better myself. Okay, I'll stop. So I have to unshare or something here? No.
No, you could keep sharing for now, and just we'll turn to questions. Thanks very much, Richard.